Guys, welcome to my recorded office hours. I will be in the Slack channel later doing question and answer. Right now I'm going to go over three different things. We're going to start off with I added some pseudocode to that Google Doc that I shared with y'all earlier on bagging. So I'm going to go briefly over the train and the query functions, and at least how I think you should make them. So given that you're given test X and test Y, let's say, and these are everybody's asking about the different percentages that you're supposed to use with bagging. So we've already split your data into 60% test, or 60% train and 40% test. So this is your training data right here. Sorry. So we have n rows or n observations. You can use two functions. I suggest NumPy random choice. Make sure you use sample or you replace. Or you can use NumPy random int. And I recommend that you select the same, you make your bags as large as the size of the training data. So here's an example of using NumPy random int. What we're going to do is we want to generate a set of rows to select from our train X and train Y data. So let's say we had 25 rows. We want to sample 1 to 25 25 times, and then here's what our output would look like. And then what you do is you're going to reuse that output, or you're going to use that output to reindex train X and train Y. And then you're going to take each of those, you're going to do that 20 times or however many bags you have, and you're going to pass those bagged data sets to your base learners, whether it's a random tree or linear regression. When you go to make a prediction, let's say you have 20 learners. For each of the base learners, you're going to call query on the set of observations, the test X. And this is just an example prediction. Let's say you have 5 learners, actually. You're going to get back, the first one says 200, the second one says 300, third one says 400, 500, 600. So you're going to take the average of all those different predictions for regression. So that's my basis of bagging. It shouldn't be incredibly complicated. The code should be pretty simple. Okay, I'm going to briefly talk about the report here. I think I covered the first bullet last time. My example might have not been that great. But if your leaf size is set to 1, so machine learning is really about generalizing from a set of data. If you make a generalization from one observation, you're not going to, be robust, or if that makes sense. So, like, let's say we were looking at stats on sports players or people playing sports, and we want to determine whether they, maybe we're baseball scouts or something like that. And if you let the leaf size get down to 1, if you have all these attributes about players, like you have what college they played baseball for, like, their various baseball stats, their RBIs, etc. But you also have their color of their eyes and how long their hair is and where they were born. If you generalize from one example, if you say get down to a leaf size of 1, and you generalize from that and say people with blue eyes are, going to be good at baseball, then you're really only generalizing off of one observation. So by keeping the leaf size larger, you're making a prediction that comes from multiple observations as opposed to one observation. This might be a little confusing because in sort of professional software packages that implement decision trees, you can control the leaf size, but usually they have other knobs which are like, say, instead of randomly making a split, say like cart trees or ID3 or various implementations of decision trees will use Gini impurity or entropy, and they'll basically stop splitting the data when it doesn't improve the performance of the model. So you don't have those knobs, so the knob that y'all are playing with will be leaf size. Okay, on to the second question. Can bagging reduce or eliminate overfitting with respect to leaf size? Fix the number of bags and vary leaf size to investigate. Again, you're going to produce, I haven't really talked about what y'all are producing, but you're going to, vary, keeping bags at say 20, vary the leaf size. And what you should see is that you should see that bagging can reduce overfitting with respect to leaf size. Now, why? I think Tucker covered this, and there's been some discussion of this on Piazza. But if you have 20 learners that each learned on a different bagged data set, each learner is going to potentially not have every training set observation. It's likely that each learner is going to get, I think Tucker did some math in the lecture that said, like, given n training observations, if you bag, on average, the number of unique observations in a bag is going to be something like 60%. I can't really remember the math, and I don't remember the Piazza post exactly. So that right there should give you some indication of why bagging is robust to overfitting, is because each learner, when you go to query and you're aggregating the prediction from each learner is going to potentially not have seen that training example, and therefore you're going to generalize off of a larger set of examples, even if your leaf size is set to 1. I hope that makes sense. And then this last one, does overfitting occur with respect to the number of bags? Choose leaf size and keep it fixed. This one should also be pretty straightforward. More bags leads to less overfit models, because even with, say, a leaf size that is relatively robust to overfitting, because you are generalizing from a larger set of observations. Okay, so that covers the report. The final thing I want to cover is regression and classification and how you're going to defeat learners. So I'm going to go over classification first, despite the fact that your assignment does not entail defeating classification learners. You're trying to defeat regression learners. But I think it's worth discussing just so people can sort of understand what's actually going on when you learn. Like, what are these learners doing? So I made this sort of mini presentation here. So all of the different machine learning techniques, we're going to be talking about classification, and we're going to be particularly talking about what decision trees do. And then when we get to the regression example, I'm going to cover sort of the differences. Well, I'll go over the difference between regression and decision trees in regard to classification here. But here's our basic our basic classification problem. We want to predict whether you're a man or a woman just given your height and weight. So we go out and we get a bunch of data. We get people on scales and measure their height, and we know whether they're a man or a woman. And then we build a decision tree. And this decision tree is not, we're not randomly picking the splits. It's using some information criteria to make the splits. For example, so we have these rules. If the person is taller than 5'7", or if they're shorter than 5'7", then they're definitely a woman. This is just an example. If the person is heavier than 120 pounds, and they're taller than 5'7", then we think they're a man. Otherwise, we still think they're a woman. So when you go to predict new observations, what the decision tree has done is it has created these boundaries that are perpendicular to your feature axes. So a decision tree, right, basically says, are you less than or equal to 5'7"? Then continue splitting. Okay. Are you greater than or equal to 5'7"? Then continue splitting. Are you greater than or equal to 120? So this region right here represents all of the future predictions that we're going to make, that we're going to say are male. And then these regions here are of the future observations that we are going to say are female. So the question is, can we do better at separating this two-dimensional space of height and weight without rules that are strictly perpendicular to the feature axes? And that's sort of the question that's at the heart of whether you would use a logistic regression, which is a type of linear regression for classification problems, or whether you'd use a decision tree. So here's the sort of space that a line would be able to learn. And I want to point out that the line can still be perpendicular. If the line is perpendicular to an axis, that means it's not incorporating the weight feature whatsoever. It's just basically a rule on height. But a single line can be our class separator. And then when you get into more and more complicated machine learning algorithms such as neural networks or support vector machines, you can basically make non-linear separators. Decision trees are one example of non-linear separators, but like neural networks are better at making smooth curves, and support vector machines are good for making, say, circles. So like if you're inside this circle, then you're a man, and if you're outside this circle, then you're a female. So moving on from that, I'm going to talk about regression, because that's really the focus of this assignment right now. I want to make a point that regression, and really all of supervised learning, in fact, is just function approximation. And I think one of the things that you need to remember or need to think about, and this intersects with a little bit of CCA, a little bit of computer science theory, is you need to extend your definition of a function beyond polynomials and lines. And really, I've given you a bunch of example functions here, right? So we have a line, we have an absolute value, we have a step function that has a couple if clauses, we have like a max function, we have a more complicated, we have a full polynomial here, and the linear regression is fitting lines to data, as I've shown here, with some certain assumptions behind the math on it. So if we have a dependent variable, an x, and we want to predict the y, a linear regression is going to fit a line through those points. These little dots are the points, and then it's assuming that the deviation from that line follows a normal distribution. That's some of the baseline assumptions